Hello students, welcome back to the session of mean life. See, in the previous video we have seen that what do you mean by half-life. So half-life is nothing but the time taken by any radioactive sample to get decreased by half of its initial number of atoms. Means if we have n0 number of atoms, the time required to reduce from n0 to n0 by 2 number of atoms, then that is what we call it as the half-life. Now we are going to study about what do you mean by mean life. So mean life is defined as, see, all the atoms cannot disintegrate at a time. So the lifetime of any radioactive sample and the number of atoms present in it, so it will be having a life from 0 to infinity. There is some atoms will decay immediately, okay, some atoms will take very longer time so to decay, okay. So we cannot predict which atom will decay at what time. So therefore the lifetime of all the atoms in a radioactive sample will be in between 0 and infinity. So therefore we have to calculate the mean life. So mean life is defined as the ratio of sum of the life of all the atoms to the total number of atoms. So this is the definition for, or the mathematical equation for, the mean life. So mean life is defined as the ratio of sum of the life of all the atoms to the total number of atoms. So this is what we call it as the mean life. Okay. Now let us obtain an expression for mean life. So mean life is usually represented as A, that is T average, mean life or average life. Okay. Now how to obtain the expression for the mean life is as follows. See, now let us consider that n0 be the number of atoms at time t is equal to 0. So initially, before the decay of the element, let n0 be the number of atoms and let n be the number of atoms in the radioactive sample at time t, that is a time interval t. Okay. Now see, now let us consider that is dn be the number of atoms that decay in the time interval t and t plus dt. So what is the number of atoms at instant time t is equal to 0 means it is n0, and what is the number of atoms present in the radioactive sample at any instant of time is t, that is n, and we have dn by, that is dn as the number of atoms that is being decayed within a time interval of t and t plus dt. So in this time interval, the number of atoms that are being decayed is taken as dn. So if we consider that is dt is very small, so the lifetime of dn atoms will be written as minus dn into t, where the negative sign indicates, that is the significance of negative sign is that the number of atoms decreases with time. So this is the significance of the negative sign. Now let us have once again the look on assumptions, that is let n0 be the number of atoms at time t is equal to 0 and let n be the number of atoms at any instant of time t, that is the number of atoms present in the radioactive sample at some instant of time t. Now let us consider in a time interval t and t plus dt, in this time interval if there are dn number of atoms that is been getting decayed and if we consider that is dt is very small, there is a very smaller value, so therefore the lifetime of dn number of atoms will be equal to dn into t. That is, in a time interval t, there are dn number of atoms that is been getting decayed. So for what amount of time is that dn number of atoms are remaining, means it is dn into t. Okay, so here the negative sign indicates that the number of atoms goes on decreasing with the respect to the time. So just now we have discussed that the atoms in a radioactive sample will have a lifetime in between 0 and infinity. Okay, that is, all the atoms will not decay at once for a time, or it may take a very longer time. So therefore we say that the atoms will have a lifetime between 0 and infinity. So what is the time period? Okay, so there is a sum of all the lives of all the atoms, means you have to integrate, there is the sum of lifetime or life period of all atoms, okay, can be written as integration 0 to infinity minus dn into t. Okay, got it, students? Why we are calculating the sum of the life period of all atoms? Because according to the definition for the mean life, it is defined as the ratio of the sum of life of all the atoms divided by total number of atoms. Okay, so now here we have calculated the lifetime of dn number of atoms in a particular time t. That is, here we have a time interval t and t plus dt. In this time interval, the number of atoms that is getting decayed is taken as dn. Okay, now if you take dt is very small, so therefore the lifetime of dn number of atoms will be taken as dn into t. Okay, now what is the number of atoms that are present in a time interval t, means it is dn. Okay, so and the negative sign indicates that the number of atoms are getting decreased. Okay, now what we need to calculate, means we all know that the lifetime of all the atoms which are present in a radioactive sample will be between 0 and infinity. Okay, so between 0 and infinity, the atoms of the radioactive element will go on decay. Okay, so what will be the sum of the time period, that is a life period of all the atoms, means from time 0 to infinity. So the number of atoms that are being decayed in a time interval t, so that is given by integration 0 to infinity, so minus dn into t. Why? Because this is a continuous decay process. So since the function is continuous, that is the process is continuous, so we have to take the integration between 0 and infinity, so minus dn into t. Okay, now if we substitute the value of t average, that is, we have t average is equal to, it is defined as the ratio of the lifetime of all the atoms, okay, divided by the total number of atoms. So the total number of atoms initially at time t is equal to 0 was taken as n naught. So therefore, according to this definition, in the denominator we are substituting it as n naught, and in the numerator we are substituting the integration 0 to infinity minus dn into t. So now we know that according to radioactive decay law, that is dn by dt is equal to minus lambda into n. So therefore, if I simplify this integration, or if I substitute the value of dn by dt in this equation, we get, or dn is equal to minus lambda into n into dt. But we also know that the number of atoms at any instant of time is given by the equation n is equal to n naught e to the power of minus lambda into t. This one we have derived in our previous video. Now substitute the value of n in this equation, we get, so our previous equation was dn is equal to minus lambda into n into dt, but we know that the value of n as n naught e to the power of minus lambda into t into dt. Okay, now substitute the value of dn in the equation. T average is equal to 0 to infinity minus dn into t divided by n naught. Okay, this was the expression for the t average. Now substitute the value of dn from this equation, you get T average is equal to integration 0 to infinity minus, and this minus becomes plus, lambda into n naught e to the power of minus lambda into t into dt divided by n naught. Okay, so T average is equal to, take lambda into n naught outside the integration, so therefore remaining is lambda into n naught into integration 0 to infinity. Within the integration we have e to the power of minus lambda into t into small t into dt, the whole divided by n naught. So this n naught and n naught gets cancelled, so therefore T average is equal to integration 0 to infinity e to the power of minus lambda into t into dt. Okay, now we have to integrate this with integration by parts. Okay, so I'll rewrite this equation as T average is equal to integration 0 to infinity t into e to the power of minus lambda into t into dt. So now we have to integrate this equation by parts. If you integrate by parts, we get, so I'll take t as the first function and e to the power of minus lambda t as the second function. So if I consider this and integrate by parts, as you all know the expression for the integration by parts, so therefore this equation can be written as T average is equal to, sorry, here we have left out lambda, so keep it this lambda as it is. So this equation integrating by parts, you get t into e to the power of minus lambda into t divided by minus lambda minus integration differentiation of first function t, it will get you 1, and e to the power of minus lambda into t divided by minus lambda into dt, right? So T average can be written as lambda into t e to the power of minus lambda into t divided by minus lambda minus 1, take out this minus lambda from the integration, of course this is between the limits 0 and infinity, and we get e to the power of minus lambda into t divided by minus lambda within the limits 0 and infinity. Now simplification of the above equation will get you t e to the power of minus lambda into t divided by minus lambda minus 1 divided by this minus and this minus plus minus into minus plus lambda into lambda square into e to the power of minus lambda into t and integration 0 to infinity. Now substituting the upper limit first and the lower limit next, so we get the expression for T average as T average is equal to lambda into t is taken as infinity because the variable is t, so therefore we have to substitute the value of t as infinity, t e to the power of minus lambda into infinity, it will be infinity divided by minus lambda. So for this we have substituted the value of infinity minus, for this we are going to substitute infinity e to the power of minus infinity divided by lambda square. So upper limit we have substituted for this entire equation. Now we are going to substitute the lower limit, so that is at the place of t substitute the value of lower limit as 0, e to the power of minus lambda into 0, it is minus 0 divided by minus lambda minus e to the power of minus 0, substituting the value of 0 here, we get e to the power of 0 divided by lambda square. So the previous equation that we had was in this format. So if I simplify this, here we get the value as 0, here also we get the value as 0, minus this equation is also 0, minus this e to the power of minus 0 means it will be 1 divided by lambda square. Now T average is equal to, keep this lambda as it is, this minus into minus it becomes plus, so it will be 1 by lambda square. So T average is equal to this lambda and this lambda gets cancelled, so this is 1 divided by lambda. Okay, now let us see the relation between half-life and mean life. See, just now we have obtained the expression for mean life as T average is equal to 1 by lambda, and we have obtained the expression for half life, that is T is equal to 0.693 divided by lambda. So this half life, okay, is 0.693 into 1 by lambda. So 1 by lambda means it will be definitely T average. Okay, so this is the relation between half life and mean life or the average life. Successive disintegration. See, suppose let us consider we have a radioactive element A. Now, if this radioactive element start decaying, it gets converted into another element B. Let us consider. Now, this element also starts decaying and it gets converted into another element C. Now, this element further decays to form another radioactive element D, and this process continues until a stable nucleus is formed. Okay, students, why radioactive takes place means due to the instability. In order to gain stability, this radioactive substance will decay into another radioactive substance, and this will decay into another radioactive substance D, and this further decays into D, and this process continues until a stable nucleus is formed. So this process of continuous or successive disintegration of one element or one radioactive substance to another radioactive substance to form a stable nucleus will be known as a successive disintegration. Clear? Now if we consider these three elements, this will be called as the parent nucleus, and this will be called as daughter nucleus or daughter element, and this will be called as the granddaughter element or nucleus, and so on. Okay. Now let us consider at time t is equal to 0, the number of atoms in A is taken as n naught. That is, at time t is equal to 0, the initial number of atoms that was present in this parent nucleus, which is taken as A, is n naught. Now, when this element A starts decaying, so after a certain interval of time, after time t, number of atoms in A, let it be equal to n1, and number of atoms in B will be taken as n2. Why? Because see, once this parent nucleus starts decaying, it will be transforming into the another nucleus or another element. So therefore, initially at time t is equal to 0, that is before the decay of this parent nucleus, the initial number of atoms was n naught. So now as the time elapses, after a time t, so this parent element A is getting decayed. Okay, so at this particular instant of time, so what is the number of atoms that are present means let us take it as n1, and when this starts decaying to the another element, the another new element is formed. So let that new element that is formed or daughter nucleus or daughter element is formed, that is taken as n2, where n2 is the number of atoms in B at this instant of time t. Now let lambda 1 be the decay constant of element A, and let lambda 2 be the decay constant of B. Okay, so why? Because we need this lambda 1, that is decay constant of element or nucleus or parent nucleus A, and lambda 2 will be the decay constant of another element, that is the daughter element B. Now let us consider, that is, rate of formation of daughter nucleus can be written as lambda 1 into n1. Got it, students? Why? Because from the decay law we can write the rate of disintegration of a radioactive element is directly proportional to n, or dn by dt is equal to minus lambda into n. Right? So here what we are considering, here we are considering the decay of element A. So when this element A is decaying to another element, means it is nothing but the formation, that is the rate of disintegration of the first element, that is dn1 by dt will be equal to minus lambda into n. This lambda, this negative sign indicates that there is a decrease in the number of atoms. So what is the decay constant for element A? It is lambda 1. And what was the initial number of atoms in A? It was n1. So therefore when this starts decaying, a new element B is formed. So therefore we can write the rate of formation of the daughter nucleus is written as, or daughter element is written as, lambda 1 into n1. We are not taking this negative sign. This negative sign always it indicates that there is a decrease in the number of atoms in a particular element. Now similarly we can write the rate of decay of element B can be written as lambda 2 into n2, where lambda 2 will be the decay constant for element B and n2 is the number of atoms or number of radioactive nucleus present in this element B at an instant of time t. So therefore the rate of decay of element B can be written as lambda 2 into n2, again by using this equation. Now the very important point that to be understood from these two equations is very important. See, we have here the rate of formation of the daughter element or the daughter nucleus B, that is written as lambda 1 into n1. What was lambda 1? Lambda 1 was the decay constant of the first element or the parent element A. What is n1? n1 was the number of atoms at instant of time t in element A. So now when this element A starts decaying to form the another element B, okay, so this also starts decaying, so therefore that rate of decay is written as lambda 2 into n2. So once this element A starts decaying into B, so there will be a increase, or there will be number of atoms in element B will goes on increases. So how it is to be measured means it is measured as a difference between lambda 1 n1 minus lambda 2 n2. So this is written as the net rate of formation of the atoms of the second element. So this is written as dn2 divided by dt is equal to the rate at which the first element is decaying minus lambda 2 into n2. The rate at which first element is decaying minus the rate at which the second element is decaying. So the difference between these two will get you the rate of formation of the second element, or it can also be written as the increase in number of atoms in B. So both means one and the same. So why? Because how the element A decays and how the element B forms. So this way the difference between these two will get you the number of atoms that can be present in element B. So this point or this stage is very important. Okay, so if you go through these equations, okay, you'll come to know what is the reason for this. So our previous equation was dn2 divided by dt is equal to lambda 1 into n1 minus lambda 2 into n2. So but we know that n1 can be written as n0 e to the power of minus lambda 1 into t. Okay, substitute this equation equal to, take this on to the right hand side, we get, so we have the previous equation as dn2 by dt plus lambda 2 into n2, this is equal to lambda 1 into n0 e to the power of minus lambda 1 into t. Now multiply by e to the power of lambda 2 into t on both the sides of this above equation, we get dn2 divided by dt into e to the power of lambda 2 into t plus lambda 2 into n2 into e to the power of lambda 2 into t. This is equal to lambda 1 into n0 e to the power of minus lambda 1 into t into e to the power of lambda 2 into t. This is the equation that we get. Now if you look into this left hand side equation, it is in the form of d by dt of n2 into e to the power of lambda 2 into t. So if you differentiate this first function, or take this as the first function into differentiation of second function plus second function into differentiation of first function. So therefore the left hand side can be written as the differentiation of n2 into e to the power of lambda 2 into t. This is equal to lambda 1 n0, bases are same, so powers can be added, positive term minus negative term. Now let us integrate the above equation. So we get, if you integrate this left hand side and this so in the left hand side integration and differentiation get cancelled, so therefore it will be n2 e to the power of lambda 2 into t, this is equal to lambda 1 into n0 e to the power of that is integration lambda 1 into n0 e to the power of lambda 2 into t minus lambda 1 into t. Okay, so now we have to integrate on the right hand side, so we get n2 e to the power of lambda 2 into t, so this is equal to lambda 1 and n0 can be taken out from the integration and we have this equation. So in this we have e to the power of lambda 2 minus lambda 1 into t, the whole divided by lambda 2 minus lambda 1 plus c, where c will be known as the constant of integration. Now let us find the value of the constant of integration. So now let us take, that is at t is equal to 0, what was the number of atoms present in A, means it was n1, that is equal to n0 before the decay starting. Okay, so t is equal to 0 means the number of atoms in element A will be equal to n0, and in element B there was no atoms because n2 is the number of atoms present in element B. So at time t is equal to 0, n2 can be taken as 0. So therefore if you substitute these conditions in this above equation, we get 0, which is equal to lambda 1 divided by lambda 2 minus lambda 1 into n0, okay, plus c, or c is equal to minus lambda 1 divided by lambda 2 minus lambda 1 into n0. Okay, so because we all know that e to the power of 0 means it will be 1. Okay, now substitute the value of this constant of integration in this equation, we get n2 e to the power of lambda 2 into t, this is equal to lambda 1 divided by lambda 2 minus lambda 1 into n0 e to the power lambda 2 minus lambda 1 into t plus minus lambda 1 by lambda 2 minus lambda 1 into n naught. So here we are substituting the value of c in this place. So therefore the resultant equation obtained is this. Now further simplifying, n2 e to the power of lambda 2 into t, this is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught e to the power of lambda 2 minus lambda 1 into t plus into minus minus lambda 1 divided by lambda 2 minus lambda 1 into n naught. So this was our previous equation. So in the right hand side, take out lambda 1 divided by lambda 2 minus lambda 1 into n naught as common. See, we have lambda 1 divided by lambda 2 minus lambda 1 into n naught on the right hand side in this first term, minus lambda 1 divided by lambda 2 minus lambda 1 into n naught on the right hand, on the right hand side of the second term. So therefore if I take out this as common, we are left out with e to the power of lambda 2 minus lambda 1 into t minus remaining is 1. Okay, now so divide by e to the power of lambda 2 into t throughout the equation. So we get n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught into e to the power of lambda 2 minus lambda 1 into t minus 1, the whole divided by e to the power of lambda 2 into t. Okay, if I divide e to the power of lambda 2 into t on the left hand side, this equation, this and this gets cancelled, so we are remaining with n2. Now further simplification, n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught e to the power of lambda 2 minus lambda 1 into t, the whole divided by e to the power of lambda 2 into t minus 1 divided by e to the power of lambda 2 into t. Now n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught. So if I take this to the numerator, e to the power of lambda 2 into t and e to the power of plus lambda 2 into t gets cancelled. So therefore e to the power of minus lambda 1 or lambda 2 into t, e to the power of minus lambda 1 into t, e to the power of minus lambda into t minus 1 divided by e to the power of lambda 2 into t. So this and this gets cancelled. So therefore we are remaining with n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught as it is, and here we have e to the power of minus lambda 1 into t minus e to the power of minus lambda into t. If you take out to this to the numerator, it will be e to the power of minus lambda into t. Now n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught. Okay, now we can write this as e to the power of minus lambda 1 into t minus e to the power of lambda 2 into t. So this equation will give the number of atoms present in the second element after a time t. Okay, so this is about successive disintegration. Thank you. Now let us move on to our next topic, that is radioactive equilibrium. See, we have two types of radioactive equilibrium. The first one will be secular or permanent equilibrium, and the other is transient equilibrium. So these are the two types of equilibriums. There is radioactive equilibrium. Now let us move on to the first equilibrium, that is secular equilibrium or permanent equilibrium. So from our previous derivation, we have obtained the number of elements present in the radioactive sample of the second element at an instant of time t is given by this equation, that is n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught into e to the power of minus lambda 1 into t minus e to the power of minus lambda 2 into t. So this is the equation for the number of atoms present in the second element or the daughter nucleus at any instant of time t. So now what do you mean by secular equilibrium? Means if T1 is very much greater than T2, that means what is T1? T1 will be the mean life or average life of the parent nucleus, and T2 will be known as the average life or mean life of the daughter nucleus. And we also know that the relation between half-life and mean life is half-life and lambda is t is equal to 0.693 divided by lambda, and t average or mean life is 0.693 into t half. T half should be 0.693 into t average. Okay. Now we can see that these two are directly proportional. So therefore, if T1 is very much greater than T2 means, then lambda 2 will be very much greater than lambda 1. So therefore, we have the equation as, if lambda 2 is very much greater than lambda 1 means, then lambda 2, see here we have taken T1, that is the average life of the parent, is very much greater than that of the daughter, or since t and lambda are inversely proportional, so therefore lambda 2 will be very much greater than lambda 1, such that lambda 2 minus lambda 1 will be equal to lambda 2. Why? Because lambda 2 is very much greater. So therefore we can write e to the power of minus lambda 1 into t, that is equal to 1. So therefore if we substitute these conditions in this, we get n2 is equal to lambda 1 divided by lambda 2 into n naught. So here what happens when you take e to the power of minus lambda 1 into t, so after a very long time e to the power of lambda 2 into t will be equal to 0 when sufficiently for a longer times. So we have the value of e to the power of lambda 2 into t is equal to 0. So now what happens? So at time t is equal to 0, n1 was equal to n naught. So therefore n2 is equal to lambda 1 by lambda 2 into n1. So n2 is into lambda 2 is equal to n1 into lambda 1. So this is what we call as the permanent equilibrium or the secular equilibrium. So what does this implies? That is lambda 1 into n1 shows the rate of decay of the first element, and this is equal to rate of formation of the second element. So this type of equilibrium is what we call as the secular equilibrium. That is, the rate of disintegration of the first element will be equal to the rate of formation of the second element, or the rate of disintegration of the parent nucleus will be equal to the rate of formation of the daughter nucleus. So therefore this is what we, or this type of condition is what we call as secular or permanent equilibrium. Now the second type of equilibrium, that is what we call as the transient equilibrium. Transient equilibrium. See, initially in the first case of equilibrium we have taken that lambda 2 is very much greater than lambda 1. So continuing with this, if we take, that is when lambda 2 is very much greater than lambda 1, but lambda 1 is not very small, okay, is not very small, such that they can be neglected. They have a sufficiently little bit higher value such that lambda 1 cannot be ignored. So therefore the term e to the power of minus lambda 2 into t will approach 0 faster than e to the power of minus lambda 1 into t. So therefore we have the equation n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught e to the power of minus lambda 1 into t minus e to the power of minus lambda 2 into t. Continuing with this equation, if you substitute the value of e to the power of minus lambda 2 lambda e to the power of minus lambda 2 into t as 0, in this equation we get n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught into e to the power of minus lambda 1 into t, right? So therefore n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n naught e to the power of minus lambda 1 into t. Okay, so this can be written as n1 because n1 is equal to n naught e to the power of minus lambda 1 into t, and n2 is equal to lambda 1 divided by lambda 2 minus lambda 1 into n1, or we can write n2 into lambda 2 minus lambda 1, which is equal to lambda 1 into n1. So this equation indicates that the daughter nucleus disintegrate at a faster rate than that of the parent. So this type of equilibrium that is obtained is what we call it as transient equilibrium. That is, whenever any daughter nucleus is decaying at a faster rate than that of the parent nucleus, then that type of condition is what we call it as the transient equilibrium. And from this equation we can write it as n2 divided by n1, which is equal to lambda 1 divided by lambda 2 minus lambda 1 will be equal to a constant always. Okay, thank you students, meet you in the next week.